All right. So today I'm going to go on and further explain some more probability concepts. So today I'm going to be explaining the addition rule. And so the addition rule happens when we have compounding events, and this is when an event has the possibility of having two or more simple events. So here I have a representation of some type of event that has two simple events combined. And as you recognize, I see event A and event B, and there is some overlap in between them. So that little section is called the intersection of A and B. So that's what the overlap is. So for example, to give an example of what a compounding event is, I can see that find the probability of either, and that's the most important word in the selection, either A or B. Let's say A is you took a survey and you said you were a baseball fan, so we'll consider that. In that same survey, they also asked you if you were a football fan, and you said yes. So if you answered yes to both questions, you fall in this little overlap. If you only answered yes to baseball, then you fall in this yellow section here. If you answered yes to only football, then you'd be over here. But there is this possibility that you said yes to both. So that's what that overlap is. So just looking at that picture, so that's why I'm going to move it over. If I want to figure out what is the probability of either A or B, and the word either has some connotation to it in statistics. So this is where probability and logic go hand in hand. And so the word either means if I choose A or if I choose B, then both of those would be considered successful choosings because I'm choosing either one of those. So let's talk about it. So if I want to choose, let's say this is the universe of possibilities, right? And I have a Venn diagram that showcases this compounding event of A and B. So here's A, here's B with that little overlap. If I want to figure out what is the possibility or what is the probability of me choosing A or B, that's really asking for what is the possibility of me reaching that area that I just shaded in. Remember, though, that I must only choose one value exactly only once or represent it exactly only once. So let's talk about that. As I shaded the whole thing, I did really shade A, and then I did also shade B, but I had to be very particular that this little area here is only represented exactly only once. So in order for us to calculate the probability of either A or B, this is where the addition rule comes into play, which means that in order for me to calculate the probability of A or B, I must calculate the probability of A plus the probability of B, but notice I shaded that twice, so I have to remove that double representation. So that's why you subtract that overlap so that you only get the picture with a one singular representation on there, and that's the addition rule, okay? Moving on, I'm going to talk about a two-way table. So in looking at two-way tables, this is where you have an opportunity to see multiple events and see overlap within them. So with the two-way table, it works to have two binary categories here. So there's horizontal analysis, there's also vertical analysis, and they both must, so this, I always like to make a comparison that this is kind of like a Sudoku game. So the two-way table is telling me, I can read this in so many ways. I surveyed 30 individuals, of which I asked them what was their gender, male or female, okay? And I asked them, what kind of phone did they use, iPhone or Droid? So for a two-way table to work, it means binary because you only have two options, either male or not male, and male, not male means female. And then in this situation, iPhone and not iPhone, we assume that not iPhone was Android. So looking at this, the only information I provided my students was I have a total of 30 students altogether. 8 were male. That's all I figured out, right? And then I also said, of those male, 3 were iPhone users, and there was a total of 10 iPhone users in the class. So they had to figure out all of these missing pieces. So 8 males out of 30 means there was 22 females. Okay, so this needed to add up. And then they had 10 iPhone users overall out of 30 students, which means there had to be 20 Android users. And then if there was 3 iPhone male users and there was a total of 10 iPhones, then there had to be 7 female iPhone users. And then we kind of work backwards and make sure that everything helps out here. So there's a total of 22 females. 7 of them were iPhone users, which meant 15 of them had to be Android. So in order for this to be checked out, we recognize that everything must add up. So I have a horizontal adding that 3 plus 5 is 8, 7 plus 15 is 22, 10 plus 20 is 30. And there's also vertical sums that need to add up. 8 plus 22 is 30, 5 plus 15 is 20, 3 plus 7 is 10. So this is the two-way table, and it gives us so many information, and I'm able to calculate addition rule on this on so many levels. So for example here, I want to find the possibility of either choosing a boy, a male, or an iPhone user. Okay, so first I look at what's the probability of me choosing a male. Okay, so for probability of me choosing a male, how many people are there in total that are boys? 8. Remember, probability means occurrence over sample size, or sample space, which is the total values in the space. So remember, probability of being a male is 8 over 30. Probability of being an iPhone, how many iPhone users did I have in total? 10 out of 30. How many of those people were both male and iPhone users? So I look at where these two intersect. So this was my iPhone users right here. This was my males. So if you remember that Venn diagram that I drew, that's A, B, and then here's that common space. There's A, and there's B. Remember, this is the commonality. So again, 8 out of 30 plus 10 out of 30 minus that overlap, 3 out of 30. So I figured out that the possibility of me choosing male or iPhone is 15 out of 30. 15 out of 30 converts into 0.5. There's a 50% chance of me selecting male or iPhone in this diagram, okay? So now, looking at another two-way table, total coronavirus situation here, I was able to say, okay, now let's say we surveyed 50 people, of which 21 were male, and they were just asking, what type of mask do you wear, N95 or fabric, right? So this was the results of this. So given, I only gave the total of 50 overall sample space, 21 male, 18 N95 male wearers, and a total of 27 N95 mask users. So notice language is really important here. So again, everything must add up horizontally and vertically. So if there was 18 male N95s and there's a total of 21 males in total, that means that 3 of them had to be fabric mask wearers. If there was a total of 50 people in the survey and 21 were male, that meant that 29 had to be female. So notice that in order to fill out the table, I'm using the complement rule, which I explained in my intro to probability video. Now, if there was 18 N95 male wearers and there's a total of 27 N95 mask wearers, that means 9 of them had to be female. So this is how we figure out that the two-way table. So now let's look at another one. So I'm going to use task 2 said, what is the probability of choosing a female or a fabric mask wearer? So let's see. Choosing a female or a fabric mask wearer means I'm using the addition rule. I always start with the addition rule so you know how to set up the problem. I then place the addition rule into context format. So I'm rewriting the addition rule, but instead of writing A or B, I'm now writing the event in the context that it's presented. So event A would be probability of choosing a female. Event B would be probability of choosing a fabric mask wearer. So plugging that into my two-way table is I take the females. So again, I'm going to circle as I do, right? And I also look at the fabric mask wearers, and I must subtract that little area. That's the overlap. Okay, so let's see. What is a female right here? Female means 29 out of 50. Plus, what's the fabric? 23 out of 50. Minus, what's the overlap? The overlap's right there, minus 20 out of 50. This simplifies to 32 out of 50, which means I take this ratio and I write it as a decimal because my context final answer is going to have this in a percent. So the probability of selecting a female or a fabric mask wearer is 64%. So now let's go into introducing disjoint events. So here in those previous examples using the two-way tables, I showed events that were compounded or joined together. There was some type of overlap between them. But I can also have events that are disjoint, where A or B don't have any overlap, and that means that the probability of that overlap is non-existent. What this means right here is the empty set. So the addition rule in a disjoint event would be here. This would be P of A or B is equal to probability of A plus the probability of B minus that overlap. But since overlap is nothing, then my formula now for addition rule of a disjoint event is probability of A plus probability of B with nothing else. There's no overlap to carry on, so it's just the sum of that A and that sum of that probability of B. Okay? So now moving on to multiplication rule. It's very important that we recognize that language is very important when we're analyzing probability, because one little tiny word can mean the difference between one completely different rule. So the big thing I have to understand here is when I'm looking at probability of event B given event A, what does the word given imply? The word given implies that event A had to occur before event B is considered, okay? So this is like the condition, okay? Also, the new notion of P of A and B means that what is the probability of event A happening first and then probability of B occurring after that? So first trial goes to event A, second trial goes to event B. And then this is the new notation here, P of B given A. So this right here says, not write it. You read this as probability of event B given event A. Okay, so the probability of event B given event A means what's the probability of event B occurring after event A already took place. Okay, and so this is what the multiplication rule says. In order for me to understand the probability of first trial going to A and second trial going to B, I have to take the probability of A times the probability of B on the condition of A after A occurs, okay? That's the multiplication rule. So let's talk about something called replacement and non-replacement. So for the sake of this class or for statistics, a lot of people get confused here because they think that replacement means I substitute with something else, and that's not what it means here. Here, the word replacement means I place back. So, classic probability analysis is the sock drawer problem, which means I have 10 pairs of socks in your drawer. 3 are blue, 4 are green, 1 is black, 2 is red, right? And if I'm choosing to replace, that means that when I choose my first trial or my first choosing, once I choose it, I record what color it was, then that sock goes back in the drawer. And then I choose again. So that's what's called replacement. What's called non-replacement or without replacement means once the first trial goes, that sock does not go back in the drawer, it stays out. So my drawer now has one less pair of sock for me to consider. Okay, so that's really important. So given this situation, I want you to find the probability of choosing a blue pair of sock, then a red pair of sock with replacement. So this means once I choose it, I still put the sock back into the drawer so that the second set gets to have an opportunity as well. So again, I always start with my multiplication rule. Here it is. And then I place my multiplication rule in context of the problem. So I'm letting my A be the choosing of a blue pair of sock. I'm letting event B be the choosing of a red pair of sock after blue, right? That's the new notion of P of A and B. So that means I must first find the probability of choosing a blue pair of sock, then multiply that by the probability of choosing a red pair of sock after I already chosen that blue pair of sock. But this is with replacement. So this is really important, okay? So let's talk about what happens there. I have 10 pairs of sock. Here goes my first trial. I try it. I choose the sock. I recognize the color of the chosen sock, and then I place it back into the drawer, which means my sample space is still the same. Nothing changed because I put that sock back in. So let's figure out what's the probability of choosing a blue pair of sock. I got a total of 10 socks in the drawer. How many of them are blue? 3 out of the 10. So that's the probability of choosing blue socks. A blue pair of socks, let me be precise with my language as well. Now let's talk about what's the probability of me choosing a red pair of socks after I chose blue, but I replaced it. So that means I chose the blue already, but I put it back in, so that doesn't change my sample size. So I still got 10 pairs of sock. How many of them are red? So 2 out of 10. So this is now my possibility. So I have, when I multiply fractions, if I have the rule that says top, top, bottom, bottom, 3 times 2 is 6, 10 times 10 is 100. That turns in, this ratio now converts into a decimal, which is 0.06. So now putting that into contextual representation, the probability of choosing blue and red socks with replacement, it's essential that we write this, is 6%. Okay? Let's talk now, this same scenario, but now we're looking at, let me just straighten this up. We're looking at find the probability of choosing blue then red, but this time that sock stays out. It does not get placed back. That's what replacement means. So again, probability of blue, first, blue happens first, right? So 3 out of 10, awesome. Remember, that chosen sock that I chose in the first trial is no longer placed back into this drawer. So now how many socks do I have in the drawer? I now have 9 socks. So what's the probability of me choosing red after I chose my first pair of blue? That means I have how many red? 2 out of 9. So now I have 3 out of 10 for the probability of blue, but because that sock did not go back in the drawer, I now have 2 out of 9. So putting this into the multiplication rule, again, always start with the formula. Convert the formula into the context of the problem. And again, probability of blue is 3 out of 10. Probability of red given blue without replacement means now 2 out of 9. Multiply that together, top, top, bottom, bottom. 6 over 90. I convert that into a decimal, I get 0.0667. So this now, it says the probability of choosing blue and then red without replacement, you have to notify us of that condition, is 6.67%. Okay? So to recap, we recognize that when I have replacement, that means when I get to put the sock back into the drawer. Sorry, let me just line this up. These are independent events, which means the first and second trial have equal amount of probability because my sample space never changes, okay? However, When I'm sampling without replacement, as in that sock stays outside after it's been chosen, it doesn't go back into the pot. These are dependent events now because after each event, my sample size reduces in size. And so now the probability of the other one is greatly affected from that sock not being replaced. So let's look at another example. In probability, you got a lot of sock drawer situations, you got a lot of dice and coin tosses. Here's another example. Find the probability of taking a dice, one dice, with replacement and rolling a 4, then a 5. So let's talk about why I put this in parentheses, but when my problem was given to me, it says find the probability of taking a dice and rolling a 4, then a 5. I have to use logic here and understand that I am not able to remove a face from a dice. So automatically, this is with replacement. There's no way for me to remove a face after one trial, so it's still going to be replaced. Like each of those faces is still going to be there, even if the amount of trials I do keeps on going. So it's with replacement, which means it's an independent event. So again, start with my multiplication rule. Plug it into the context of the problem presented. So my event A is rolling a 4. Event B is rolling a 5 after I rolled a 4. So probability of A is probability of rolling a 4. So a dice has 6 faces, and only one of those faces has 4 dots on it. So that means there's only one face that has 4 dots out of the 6 faces that the dice has. So that's the probability of rolling a 4. Probability of rolling a 5 after a 4, given that this is replacement, these are independent events. So probability of rolling a 5, there's only one face on the dice that has 5 dots out of the 6 faces. Multiply these together, I get top, top, bottom, bottom. 1 times 1 is 1. 6 times 6 is 36. So this is the ratio of that probability that gets converted into a decimal. And then my contextual representation says the probability of rolling a 4, then a 5 on a dice is 2.78%. Now, to prove the validity of the multiplication rule, I was able to recreate the space of rolling a dice twice, which is pretty much what this scenario is bringing up. And so these are all the possible outcomes of rolling a dice twice. Remember, I can roll a dice the first time I get 1 dot, second time I get a 1 dot. This does not mean 11. This means first trial gets 1 dot, second trial gets 2 dots. 1 dot. Here, this first trial gets 1 dot, second trial gets 2 dots, 1 dot, 3 dots, 1 dot, 4 dots. That's what it means. So I was able to break it down into all the different possibilities. And if you notice, there's a total of 36 items in my sample space. And so that's right here, represented right here. And how many of them have a 4 first and a 5 second? Only one. This right here says I roll 4 and then I roll 5. So 1 out of 36 is right there, and it still proves that my multiplication rule is valid. So I hope you enjoy probability into a deeper analysis. Stay safe, everybody. Hope to see you soon.